So I work with a smaller group within the TRCA called the Sustainable Technologies Evaluation Program. Conventionally, the program has been all about water technologies, which is what you would expect from the TRCA: swales, bioretention ponds, those kinds of things. And then they formed a new group now, which is what I'm in, which is renewable energy or sustainable technology evaluations. And within that, I work pretty much on the technical end, the hardware end of that, and the generation. So the statistics that come out of what makes a difference and how an array is going. In this case, array. We work with wind and solar hot water. We're going to be doing a study on this building, which has a solar wall. So we try and do this, provide technical information to events like this. The Sustainable Technologies website, if you go there now, it is primarily, you'll find water-based things. But as time goes by, you're going to find more and more there on the energy parts. Now, what we have done is partnered with the Toronto Atmospheric Fund and the City of Toronto, and now we have the SolarCityPartnership.ca program, and that's where we'll be doing a lot. Right now we have 14 evaluations of systems underway, and a lot of these are with city systems. So the city, of course, is both in Mississauga and in Toronto, are willing to share the information of the production numbers of their systems, but we're also looking for private partners. So one of those systems is, say, the Loyalty One system. So this is a company that's willing to share what the revenues are, what the actual yield of the system are, and then we can write a report, and then those reports will be available to the general public on the site. So that gives you a little bit of, it's a third-party evaluation, so you can look at and you can say, okay, proponent, you're telling me the yield from this system is going to be this, but I look at all these other studies and they look fairly similar to what you're putting in, and the yield is this. How come yours is going to, give me an extra 10% or something? Unless they can justify why that is, then you have to start asking questions about, okay, because it's a very soft thing. It's the sunshine, is your resource. It's free, but you've got your capital utilizing that energy, and that conversion rate, that yield, is very heavy on your bottom line, right? Anything that changes there, that's going to affect your financial, anything on the solar yield is going to affect your financial yield directly. It's a very, it's not just one of the inputs, it's the input. So one of the early studies we did was the Horse Palace, and at the time it was a big project, 100 kilowatts, and we started this study in 2008. And for example, so that's available on the Solar City website. It's also this report's also available on the Toronto Atmospheric Fund website. And so people have actually told us that they've actually literally taken this study to the bank to finance their systems. And Loyalty One is one of those systems, which is now, I think, still the largest rooftop system in Canada. And because it's third party, and it's been running for long enough that you go, yeah, it's not a flash in the pan. These are the solid numbers that come out of it. You can go and look at live data from that site. So there's a nice portal that you can access through the Exhibition Place website. So what we're going to do is just go through some of those notes, and you go, well, 2007, that's kind of old stuff now. We've included some updated information in there, but the sun last year and the sun the year before that was, we're still on the same planet. This gives you an outlook of, this is a bit nerdy, but it's just showing that we've got 4 different systems there. And I would say systems number 1 and 2 are now a bit dated in that the inverters that were used on those do not have the kind of efficiencies that a modern inverter of that size would. However, systems 3 and 4, the inverters that were put on there are still state-of-the-art inverters. So as we go through, I'll tend to look at the numbers 3 and 4 a little bit more than the first ones. So if we look at the yields, this is the standard way that I like to look at what does a system produce is the number of kilowatt hours per installed kilowatt. And this then makes it equals all different kinds of systems, all different sizes of systems together into one unit that you can look at. And so the round number that I always tell people, it's 1,000 kilowatt hours per kilowatt installed. And there you can see why I'm saying those numbers. Now, the inverters 1 and 2, you can see they perform a little bit lower than the others, and that's basically, that's the inverter. And you're not going to be buying that inverter now, so maybe looking at the systems 3 and 4. And their system 3, you can see, is still bumping in a little bit below 1,000 kilowatt hours per kilowatt per year. But it's a 0-degree array. So that's as bad as it gets, basically. Generally, we tilt them up. However, we have to remember that the fuel is free here. So efficiency isn't necessarily top dog, right? It's cost effectiveness. So if you've got a building that has zero capacity as far as weight goes to carry an array on the roof, now you have to build a superstructure over the roof. So this is, again, Loyalty 1 example. And if you look at the cost of that superstructure to make the angles, the modules tilted rather than flat, it may not be the most cost-effective way of installing the system. So this is what you're basically relying on a proponent that's coming to you and saying, we'll design a system for your roof. That's part of the little dance that they have to do is, well, do we put in more? So as soon as you go into an angle, now your dynamic loading on the roof happens. The modules start looking like snow fences, so they can increase snow accumulation compared to an array that's flat, which doesn't cost, yes?
So looking at this graph, you can tell that the difference between a sloping and non-sloping is around 15% or so.
That's right.
Which is a substantial premium when you talk about it in capital terms. The type of structural rate.
That's right. So and when we do the long-term report on Loyalty 1, we'll know, that will show whether they made the correct decision that mounting them flat was more economical than getting the extra production of putting an angle. It looks, they did their math, and I would guess they're going to be pretty close. But again, it's at this point, FIT is a relatively rich program, okay? So you can still make money and maybe have your yield off, let's say 3 or 5%. But I think as time goes by, what we're going to find is that the program will become a little skinnier, and then it will become more crucial that we get these numbers right. At this point, I think there's still enough room in the revenue that we can go, well, maybe we didn't get it quite right, but the project is still considered a success. Yeah.
For the 4 systems that you have here,
yeah.
Did you guys clean off the snow in the winter?
No.
So
no, and generally that's...
would sit there covered.
That's right. So let's carry on, and I'll show you some pictures of exactly what that looks like. We've got, the thing that happened with these inverters is they were built, designed and engineered in a time before a certain rule change happened. And when that rule change happened, isolation transformers were required for the particular topology of the way those inverters were engineered. So we had to add isolation transformers, and they cause a loss. The thing that we're seeing right now, and I think it's about to come to an end, is that one of the inverters that's quite often used in systems in the GTA is an Ontario-built inverter, but their market is the US. So they build them at 450 volts rather than the 600 volts that we have. So we have to put a step-up transformer on them. So I think they've now that the program has been running for a year or so, that they are actually going to reintroduce their 600 volt version. We won't need that step-up transformer anymore. But one of the funny things that has happened is various systems, the utility has put their metering one side or the other side of that transformer, depending on actually on the system, because within the Toronto Hydro, sometimes they've put their metering on one side of that transformer, and sometimes, so if it's on one side, it's their loss, if it's on the other side, it's your loss. So that's one of the important things to figure out in the design of the system. Where's that going to be? So that's part of your engineering. Now, we move along probably in a year from now. If you're sat here right now and you don't have a system in the works yet, this will probably be all, gone, because we'll have 600 volt inverters going in. But it's one of those things that can, that you think you've got it all down, and then suddenly 2% of your yield goes away because you've got a transformer between your system and the network. So I was called in to look at this system in 2007 because it was not performing right. There must be something wrong with this system because its yield was about 20% below what the expectations were. So what I did is I ran the 3 models that I feel comfortable with. These are, Ret Screen is pre-feasibility study software, okay? It is not design software, it is not what your financials should be based on, but this is what should set you up as to making a decision as to whether you want to have an RFP or something like that you can use this software. Before that, it doesn't have enough granular inputs to give you the detailed, information to really do a financial, you don't sign you don't sign the check until you've done something more than that. But here we'll look at what we can get. So what they had done is used Ret Screen with a 5%, what's called there's a place in there for miscellaneous PV array losses, and the default is 5%. Well, over history, I've learned the number to put in there is 17. And then that gives you more realistic outputs. And that's not a fault of Ret Screen. Ret Screen is an international-based piece of software. It comes in 57 languages. So, yeah, when you asked about the snow, if you click on that module where you enter the 5% and the little bubble shows up to the side, one of the inputs is you may want to make this higher if you've got snow and if you've got dirt. So dirt is kind of a California thing. Snow is kind of an Ontario thing. You have to bump it up for both environments. So what does that 17%, where does that come from? So if we break that 17% down, there's a nameplate tolerance. So let's say you buy a module that's 100 watts. Well, plus or minus 5. Okay, so the thing is, so some of them are going to be minus 5. And the way arrays work is if you put a -5, so a 95 watt module in series with a 100 watt module that's actually 100 watts, they both act like 95. And then if we put those in series with another one that's actually the +5 is a 105 watt module, they all act like 95 watt modules. And that's just the nature of the beast. And typically on large arrays, we're putting about maybe somewhere between 6 and 10 modules in series. So you can pretty much bet that there's going to be one in that string that's at the bottom end of the tolerance. So yes, you think the nameplate of the array is 100 kilowatts or whatever it is, and knock 5% off there. Now, maybe you might get lucky and they're all +5, right? But that's not what I'd want to count on if I was trying to finance this. The inverter and transformer, okay, so that I think that's pretty, there's a bit of a loss there, changing your DC into AC. Mismatch, okay, this, and you kind of go, what's this guy going on about? Like, these are 1%. That's 1% of your yield. So it's not just one small input. That means if your output, what your revenue is based on, is going to be down 1%. And so if, in the world of finance, that's a lot of money, right? But, so we have to, look, this is what the elements that go into mismatch. Okay, they're both 100 watt modules, fine. But one of them has a power point of 50 volts. And the other one has its maximum power point of 51 volts. Well, they're both held at the same voltage. So again, we have this series element of where we put all these modules together. Yes, they're both 100 watt modules, but it's at slightly different voltages. So that's where mismatch comes in. Connections, the wiring, the AC and DC wire, and then we come into the dirt and snow. We put in 5% there. The one element to remember is the flash test is good as far as it goes. But what does the flash test measured in? watts, right? It's a 100 watt module. What is your revenue based on? Watt hours, right? So a flash test is just that. That's how the module performs under a certain set of conditions. So what we find is we could have, let's say, two 1 kilowatt arrays, STC, standard test condition arrays. Their yields will vary plus or minus 5%. That's kind of the normal range between modules. So what that means is that different modules behave differently at different atmospheric conditions. So even though a standard test is 1,000 watts per square meter, 25 degrees C, at a light color of 1.5 atmospheres, but that's not where they live. They don't live on a test bench. They live on the roof of this building, which right now might be only receiving 200 watts. Well, two modules that flash the same at 1,000 watts per square meter may perform differently at 200 watts per square meter. And so if you're in an environment, as we are, that has a lot of low light, then one module may perform better than another one overall on yield. Whereas if they get hot, right, as modules get hotter, their performance drops off. And the one that's let's say there's one that's very temperature tolerant, it's a great module to use in California. Whereas one that's slightly better at low light conditions is maybe the one that'll win in the market here. So as good as STC is, that you can generally compare, but be careful, they don't all have the same tolerance. Right? Some manufacturers are -0 plus 5. Some manufacturers are -10 plus 10. So that's on the STC number. So STC is good. And that's why, we'll see in a few minutes here what we're doing at Courtright to try and give you information. Because just because one module is slightly less, but maybe it costs less. So this is where the cost effectiveness comes in. So don't forget, it's always good to ask the question as to how efficient it is, but don't forget to relate it back to cost effectiveness always. So this is how the systems did according to the actual numbers, which is kind of that darker purple line, and the red screen predicted this is what red screen predicted. So that's why the system wasn't performing correctly. It wasn't that there was anything technically wrong with it. It's just the wrong model the right model was used just with the wrong input. So garbage in, garbage out, same old story. So that's basically was once people saw that, and I said, that's what I would have predicted for that system. They went, oh, okay, because up to that point they were beating themselves up, going, what's wrong with this system? How come, But there it is. So you got to have the right expectations going in, and that's where all this information about how they compare our atmosphere matters, because those are all the inputs that we're looking for in these models. And that's how the different systems did over the year. Obviously, we have 1.2 sun hours in December, and we have like 5.6 in the summer. So basically, systems do 5 times as well in the summer. So that's why this kind of shows, as much as we think that our modules need to be tilted, you make hay when the sun shines. You have the modules tilted towards the sun here. Don't worry about this. Now you might have even heard, okay, there's this rule of thumb that says modules for best year-round production is 45 degrees. That's purely a mathematical calculation that does not take into account weather, right? That's just, we're at a north latitude, and if it was clear all the time, year-round, 45 degrees would be the best. But let alone do we have short daylight hours, we also tend to have a lot of overcast skies. So basically, what happens here is not so important. It's being at the right angle for there. So, that's where optimal angles are probably, for efficiency, 30%. But that doesn't mean cost effectiveness is best at 30, maybe it's at 20. On this one, what I wanted to show was that even though I put in, say, a good D-rate factor into ret screen, these models still have a hard time predicting what any month's production is going to be. So you can see that it's under, what's happening here and here is opposite. So the systems tend to overproduce according to the model in the summer and underproduce in the winter. So long as you've got a year before you need to make any decisions or before you start getting worried that your system isn't producing properly, you're okay with that. But quite often, if you've just put down a chunk of change after the first month of production, you want to know how the system's doing. Well, unless you're using a slightly more intelligent model, unless you're here or here somewhere, the model will be either over or under predicting what should have happened that month. Local installation, what really happened? Okay, I've got an array and I've installed it and I used a good model to predict, and let's say I'm 10% low that first month. Is something wrong? So you've got the question is, okay, my model is built on a 20-year average. What was the sunshine like in the month that I'm looking at? Right? So if you've just, you've just commissioned a system, you're looking at your first months of information, and you're over 10% and you're under 10%, that's about the range it'll be. That's the normal variation for the 20-year average. So you now need to know how much sunshine was there in the last month, and how do I compare that to, how does it compare to the 20-year average? So what I want to do is I want to have some on-site pyranometer to measure how much sunshine landed on my system, and then I can know where I land. And was this an average April, or was this above average April? Well, if it was an above average April and my system is below average performance, what happened? And so what you want to do is have that on-site pyranometer. Now, unfortunately, this is Horse Palace. This is what a $300 pyranometer will do for you. And this is what a $3,000 pyranometer will do for you. These all agree with each other, and this guy's off. You can see that you would have thought that we didn't have very much sunshine, and that's why the system didn't produce very well. So unfortunately, it's not highly informative to put relatively cheap instrumentation on site for every site. These can be good, or they may not be. It's just they tend to wander around a little bit. And it can cause alarm or euphoria where it's not warranted. You go, woohoo, the system's doing great, and we had, minus 10% over the 20-year average. It's a wonderful system, I'm gonna make a killing. Where what it really is it's just not a very good instrument. So that's why one of the projects on the Solar City assessment, and that you'll start seeing reports on a monthly basis on that site, is we've started up a network within the GTA of all of these instruments, and they're all going to be posted. So that you'll be able to go there and go, or your vendor will be able to go there and go, aha, it was a perfectly normal April. So this is what, I think this is now your question. So if we look at the red screen 20-year average, that's that nice dark blue line that is kind of on its own. It's right there in the middle, and it has a nice bell curve to it, right? It's got a nice shape to it, which is the sort of thing that happens when you do averages, right? You get nice smooth curves. However, we can see what the year really did. This month, we're totally below normal, or average, I should say. I would say this is a very normal month. It's just below the average. And that is well within, when we look at the statistics of these things, that's well within the norm. Plus or minus 10% for any particular month is normal. Just like rainfall, plus or minus 10% rainfall, the same thing with sunshine. But you know what, it's kind of neat that you kind of go, hey, the planet kind of has this correcting factor. Because if you go along to month 13, I like to call Sunuary, this is the yearly average. So this isn't a real month. you know what? Over the year, we tend to end up on the 20-year average, year after year after year. So just because I've got an underperforming system here doesn't mean I should get all excited and you know, say, hey, I want money back. The weather systems tend to normalize themselves by, if it's a rainy month here, it'll be a sunny, you know, it was a rainy spring, it's a sunny summer. So if we've got a year to sit back and let the numbers pile in, we'll generally find ourselves always at this point. And these two here, this is the X-Place pyranometer, the original one has been replaced. You can see it was reporting low. And this is another very expensive instrument, but it was only calibrated over this period of time here. Here, they weren't using it. So that's why very expensive instruments, you then got to maintain them. And that's why you don't, even if you got the bucks, you don't necessarily want to plunk one on the roof of every building, is we have to take these things in and have them calibrated. Unfortunately, sunshine is a relatively easy thing to measure, but if you want to be this accurate, it takes more expensive instruments. They're on. And there it is statistically, that's kind of boring. Business case, this isn't all that applicable because of course this was a RESOP system at 42 cents. You can just look at that and go, oh, aren't we good? We got 70 cents now. So like I said, we've got 14 systems on the go. We have a solar energy best practices guide on the STAP website, so that's available to you. The solar radiation network, when we have it all calibrated, we'll start reporting to that site. And what we hope to do is actually have an evaluation tool that you can put your systems in on. You'll have a monthly solar correction factor, and you'll be able to just load your system in there, and you'll know how it's doing. So these are a bunch of sites where we're doing studies. One of the inputs that is not typically done is an obstruction or shading analysis. And so this is a fairly old instrument, but I like it because it makes it very visual. You can see that there's a chimney here. Okay, and that's going to shade that part of the array for certain hours of the day of certain months of the year. And then there's the X-Place array, and you can see these points here demarcate where I used the instrument. So I used it at the four corners of this section of the array, and that's where it picked up that flagpole and that chimney. So we just have that as an additional input. Now, a lot of people will go, well, I actually have no obstructions. There's no chimney and there's no flagpole. But everybody has a horizon. And so if we go, well, okay, because the solar radiation data, my instruments are on a pole above in the middle of a great big field, right? So that's how we take the measurements. You go, well, there's just buildings around me. Well, let's say they take off 0.25% of the sunshine. That's 0.25% of your yield. It's 0.25% of your income. And when you look at financials, that's the kind of number you look at. But on these models, people tend not to go, well, you know, it doesn't matter. It's only a little bit, but no. Just to go, here's in the back, you can see a 10 degree here, a flat array here, and a 20 degree there. This will tend to sit like this all winter, in fact be buried. Well, this one will tend to clear itself. That's the kind of thing that models don't take into account. So that's why, and it's a very regional thing, you know, how does the snow fall and hold on to different angled arrays in the GTA. And so what we have at Courtright, and this was going to be a time-lapse photography, but I guess this computer doesn't read it, is we have arrays 0, 10, 20, 30, and it goes right across to vertical arrays, and we're taking actual numbers off of these. So that's where, you know, that will again be inputs that are available to you and to people in the industry to make predictions as to what yields will be on different angles. Now, here's two images at a certain timestamp, and what you can see is the 0, 10, 20 degree array has shed its snow except for this one little bit. And this isn't so informative as far as snow goes, but here is my data for those two modules. At this point, this one is producing 60 watts, this one's doing 16. That much shading basically shuts down the module. So from an inter-row shading issue, from a flagpole, from a chimney kind of issue, that's the sort of impact that shading can have on modules. So we almost come to the end here, and yeah, I'm doing pretty good. When the X-Place was all said and done, and I was actually just going back for another, just a physical look around the system, you can see a nice picture that I took after saying what I just said about shading. I thought it was kind of cute that this little tree was trying to grow up in front of this module, and I thought, well, I'll just have to wait that for to grow high enough to cause a bit of shading, and it'll make a good picture. And then on the way home, you know, grade 10 biology kicked in as, okay, a tree growing, moisture, food, you know, hang on, it shouldn't be growing there. So I actually had to turn around, drive back, and go, well, what's going on here? And you can see this is the ballast on the roof, right? Just the gravel. That's the rack, and that's the module. No gap. In the lower picture, here's your ballast, here's the rack, here's the module. Whoops, there's a space. So it just happened to be that these modules in that racking system caused the module frames to fill with water and split. So on the one hand, there is risk, and you know, and that was, hey, they just had, after we saw that, they had to go around and drill some drain holes in there. Problem solved. They replaced the modules that had been damaged. Just bringing that up as there's risk, and every time you change the technology. So as you're looking to vendors, what was your last system? You know, so this is where I know it's a new industry, and a lot of people don't have a lot of experience. A lot of the vendors won't have put in a lot of system. But boy, I'm going to give some, in my evaluation, I'm going to give some weight to vendors who have some experience, and in particular have some experience in the technologies that they're installing on your system that you're financing, that you're going to own. So that's just a word of caution on the one hand. On the other end, under risk management, all renewable energy technologies basically fix your energy costs. So in a way, they take away risk, right? So as much as I know, you know, the FIT program and PV is doing great these days. Look at all the solar wall, solar air, that's solar air heating, the solar thermal systems, and think of that as you evaluate those technologies. Essentially, every time you spend capital to harvest energy, you're fixing your energy costs into the future. And it may seem a bit high, but if, say, you're putting in a solar hot water system and it's displacing gas, you know essentially what you're going to be paying for gas in the future. Just like buying a gas contract, it's a little bit higher, but it's a fixed cost. Renewables do the same thing for you. It might be, the energy might look a little higher, but you're fixing your costs. And of course, if you do, I wouldn't do maybe for 100% of your energy requirements, but if you add that into your mix, then your bottom line isn't as volatile when we're moving into times like we seem to be right now, where energy prices are possibly doing some of this, or maybe just that. The things that I've been talking about seem to be a little nitpicky, but they affect the performance of the system every day of the year, all day. Whereas you can have larger variances that happen for a few hours, once in a while. So maybe it's, you know, shuts the system right down. It's not going to, but let's say it does that for 4 hours of one day in the year. That really doesn't affect your bottom line.
No, but it's the soot that
Oh, the soot. Yeah. Well, yeah, there again, I mean, if it's in an urban environment, I can't imagine that there's going to be you can clean them. It's generally not worth it. In California, they do clean them because it is worthwhile, but in the environment here, even in the summer, we get thunderstorms. You just wait till the next thunderstorm, it cleans it off. So I wouldn't worry about it. I wouldn't worry about that part. And certainly the modules are very tough. I mean, it's glass and anodized aluminum. So the ray itself is a very durable element.
So should we be using some derating factor for the output?
Sure, and I would expect rather than you doing that yourselves possibly is that any vendor who is proposing a system that you're just making sure that they're doing those kinds of things. So where I said, you know, my answer to is how much energy, I say 1,000. It is quite reasonable to see systems, like I know of systems that reliably do 1,200. So that's 20% more. That's the top of the limit of systems that I know about. So if someone, a proponent for that fire station is saying, the system is gonna deliver 1,300 kilowatt hours per kilowatt per year, I'd really wanna know, okay, how's your system gonna pull out that kind of magic? Whereas if it's in the range from 1,000 to 1,200, I think they're well, and I realize that's a big range, that's a 20% variability. But what I say is where the program is right now, it's 70 cents for Fed and, at microfit, there's enough fat in that to have 1,000 watt kilowatt hour system pay for itself. And that's always the way to look at it. I mean, just, hedge your bets and, do your finances on 1,000, and when it turns out to be 1,150, hey, your profitability just went up. Yes?
I have another question regarding the irradiation over long term. So currently all the models are looking at, what's the average over, the last 20 years. But I know from my own experience that the last 20 years might not be a good predictor. We have the experience with the wind in Germany where we built a wind farm in '99 based on the 20-year wind data, and it turns out now 30 years later, 12 years later, that was overly optimistic because those 20 years we built the farm on were better than the next 12 years we have now. So, and that's 15%, so that's a huge number.
Yeah.
So I wonder, and that's due to climate change, obviously, so since you're doing research.
So you saw the graph there that had the 20-year average, and what you might assume is we're using the last 20 years. No. We're using information that was gathered by the federal government on the energy crisis that I started in the industry for, which was about 1976. So we're talking about 20-year-old, the end of their 20-year average period ended 20 years ago.
Yeah.
And so you see how that 20-year average, that's now that data, the newest of that data is now 20 years old, came right on to what we're seeing now. So yes, I would agree that things like wind seem to be more variable, and insurance adjusters will tell you that. But it seems that the solar is not changing that much. Maybe it is, but it's got to be in the less than 1% category, I would think. So at this point, who knows where we're going? Of course, that's the problem with, conducting planet-wide experiments. Who knows what the result is? But at this point, we can still use this 20-year-old data. So that was actually brought out as one of the reasons why we thought the X-Place was doing poorly, because the pyranometer was showing poorly, that we in fact don't, and it's downtown kind of, and it's on the lake. All those things were kind of rolled out, and I looked at them all one after another and came to the conclusion the instrument was no good, and the model was no good. But you know what? The 20-year-old data set is just fine.
Worthwhile to talk about the manufacturers of the solar panels? Is there...
So you're looking at a 25-year warranty usually. It's kind of nice that it comes from a company that's been around 25 years, if you can, right? So, there's that. And they tend to buy each other. This is a very volatile marketplace. We've been through various iterations of its oil companies that own PV companies. Right now, what we're finding is, again, a move into the electronics manufacturers. So companies like Sharp and Sanyo, so kind of the big consumer names, they're in it. Having said that, we've got Ontario content requirements, right? So anyone who's not building in Ontario, they haven't been doing it for very long. So that one has kind of been, as much as I've always said that, there's used to be like 5 big companies. Now we've got to look at Ontario content. So who's behind it? So you might be going, okay, the head physicist Where did he come from? What's his history? Is he new to photovoltaics, or is this a guy who's, you know, worked for Shell and Siemens and, you know, and all the iterations of that family line before that? I think that's kind of where we're at now, is we have to look, you know, is it a standalone company, or is it, say, you know, like I've heard there's, you know, words of, say, Mitsubishi coming and you know, manufacturing. Well, yes, it's a big company, well established in many industries, but they're new to photovoltaics and they're new to our market. So, you know, I'm afraid there isn't a real easy answer on that one, because the Ontario content has kind of thrown that, which I'm totally for. But on the other hand, you got to recognize that Ontario doesn't have heavy-duty semiconductor manufacturing, you know, industry. You know, that went with Nortel. So we got a lot of new companies in an area where there isn't a lot of infrastructure, and so we have to, you know, this is, you know, as much as I've given you a lot of information on due diligence as far as yields go. Yeah, if the module fails in 5 years. Now I'll tell you though, the modules, like I've worked for distributors and stuff, I can say I've only ever really seen maybe 10 modules out of thousands that have actually failed. We tend to have them so that if they do have a failure, it's fairly early on. It's just like any other electronics. Infant mortality is fairly high in electronics. Of the failures, you know, if there's 1% failures, most of those are infant mortality. And I would say typically photovoltaics runs below the 1%. So of technologies that you can buy, it tends to be very robust. Now when we get into thin film, I'm talking crystalline, when we get into thin film is awash with companies that haven't made it. So that's the, you know, but typically if you're looking at a rooftop solar, you're probably, well, it depends, the market's really changing. The large PV farms that are going in, you know, down around London or, you know, Windsor way, it's all thin film. So thin film's coming. Some people are comfortable with it. We haven't seen it in the GTA marketplace too very much. Did that help you?
Yeah, I've been quoted on Westinghouse.
Yeah. So Westinghouse, now that used to be Astropower. That's former Astropower modules, I believe. I think that's where Westinghouse modules come. So there's a lineage, right? And there's people with that lineage. I'm not the best financial guy there. I'm more on the yield and technical end. The number I've always used for a long time is $10 a watt installed. Now, we are now down more around $4, right? So, but here, so where would you be? Yeah, $6. So, yeah, for rooftop, yeah, that's more where things seem to be coming in now. So when I say $10, I'm rounding things off to the nearest decimal place, right? and so you can tell where I am with the financials, but I think the comment of $6 is entirely reasonable. I hear the big stuff goes in for just under $4.